Okay, in this lesson we're looking at some features of a transverse wave, and then we're looking at a few other definitions of the things to do with waves. All right, so first of all, crests. Crests are the high points on the waves. All right, and then troughs is the opposite. They're the low points on the wave. All right, and then the next thing is a wavelength. So if you take between two corresponding spots on a wave, so there what I've just marked in is two crests, that's a wavelength. Here two troughs next to each other, so again they're wavelengths. So if you take this point here, then the corresponding point, so sliding down on the wave, is over here. So that's again also one wavelength. Now the wavelength, as it says down here, the Greek letter lambda is used to represent a wave. All right, the other thing that I haven't mentioned that's marked here is amplitude. So that's from our mean to a crest, so that would be an amplitude. Also from our mean to our lowest point, the trough, that would be an amplitude as well. So here's another diagram. This one's in your notes as well. So again, the amplitude, as it says, is the maximum displacement from the mean position. And so here over here does the amplitude. Now the wavelength, there's a few different wavelengths marked on this particular diagram, and as I said, between corresponding places on a wave, that's one wavelength, so it doesn't have to be a crest necessarily, but you need to be going the same point on the wave. Alright, so there are some definitions of different parts of transverse wave. The next thing we're going to look at is what's known as period and frequency. Alright, so period and frequency. So first of all, frequency. So the number of vibrations, cycles, waves per second. Alright, so we can do the frequency is your number of waves over the time period. Alright, to work out the frequency. Alright, so there's a few in your notes there. There's that formula that goes in the spot, but there's also some other explanation as to what the unit is, which of course is hertz, H little z. Okay, and so that's the one that's used, and there's other things, cycles per second, etc. But hertz is the one that we need to use. Alright, period. Period is related to the frequency, and period is the time for one wave, cycle, etc. Alright, so the symbol, of course, is big capital T for the symbol, and the unit is seconds, because if it's the time for one wave cycle, then it's got to be seconds. And it's related to the frequency in that the period is 1 over the frequency, or if you like, you can rearrange that, and the frequency is 1 over the period. So 1 wave, the time for 1 wave. All right. So the next thing that we are going to look at is an example. So here's the example. Example, student has a laser long heavy rope in a straight line across the floor. She holds one end of the rope and shakes it sideways to and fro with regular rhythm. This sends a trans wave along the rope. Another student standing halfway along the rope notices that 2 crests and troughs travel past him each second. Alright, so A, what is the frequency of the rope? Alright, so frequency is the number of waves over the time. Now, when we read that last bit, notices 2 crests and 2 troughs, so a crest and a trough would constitute a wave. So if there's 2 crests and 2 troughs, so there's 2 waves, and then it says each second. So each second, so whenever they use the term each second, what that refers to is 1 second. So the frequency would be 2 hertz. All right, part B, what is the frequency of the vibration of the source of the wave? All right, now I haven't talked about this in any great detail before, but the key bit to this is the student's holding the rope and shakes it sideways to and fro with regular rhythm. So it's actually the source, in this case the student, that sets the frequency. So if Freddie the halfway down's having a look and seeing that frequency is 2 hertz, then the girl who shook it, she is the one that set that frequency in the first place. So the frequency is of the source is 2 hertz. All right, and part C says, how long does it take for the student to produce each complete wave? All right, so here's that kind of term, each complete wave. So each, again, 1, so we're talking about 1 wave. And the time for 1 wave is what we call period. And that is equal to 1 on the frequency, so 1/2 a second. All right. Now, there's a thing called the wave equation. And there's a video on the wave equation. You should, of course, watch that. Alright, what the wave equation does is it links the speed of the wave, the distance it's travelled, and the time all in the one thing. And so what the wave equation says is that if we're looking at, we know that speed is distance travelled over the time taken. Now, in the waves, of course, if I think look at the distances, say, being 1 wavelength, then that time then would be the period. So the speed of a wave would be the distance, 1 wavelength, over the time that it takes for that 1 wavelength. But remember that frequency is 1 over the period, so we can replace the 1 over the period in the equation just above with the frequency, and when we do that, we get that speed is the wavelength times the frequency. So V equals lambda f, and that is the wave equation. Okay, so it tells us about the speed of the wave in relation to its frequency and wavelength. So if we've got two of those, we can work out the third. The unit, of course, for the speed is meters per second. All right, now there's a little bit of a note that I'll put on the next page. All right, so these are things that are important to remember. So when we look at that, so what determines how fast it goes, the wave travels? It's the medium is the determining factor for the speed. All right, so, and then if we go, and as we'll see later down the track in this, if waves travel into another medium, then the speed will change. That's what happens when refraction occurs. We'll get to that. All right, so the median is the determining factor of that. And the frequency is determined by the thing making the wave. All right. So in our example, it was, Joanna who was waving the rope. She determined the frequency. All right. So, and as we say, after they produce, the frequency does not change. Remember, it's vibration, so we've got to somehow change that vibration, and so it doesn't change the vibration. The only way you can do that is change the way you produce the wave in the first place. All right, so let's have a look at an example of the wave equation. Okay, so we've got a person standing on a pier. Notices that every 4 seconds, the crest of a wave travels past. The crests are 12 metres apart. All right, so we've got a couple of things from that. So first of all, crests being 12 metres apart, it means that the wavelength is 12 metres. A bit above, every 4 seconds, the crest of a wave. Every 4 seconds. So a wave goes past, a crest goes past, 4 seconds later, another crest comes past. So that's one wavelength in 4 seconds. So that's the time for one wavelength. So what that is the period. All right, so that's the information we've got. So frequency, remember frequency is 1 over the period. So 1/4 of a second. B, speed of the wave, V equals lambda F, and the lambda is 12 times 1/4, and that would be 3 metres per second that our wave travels. Now, those of you may have noticed I made a bit of an error here with my units, because for frequency it's not that. Frequency it's hertz. All right, so well done those that have picked that up. All right, the next bit, Doppler effect. All right. So we've met the Doppler effect before last year. Alright, it's a bit messy, we'll leave it like that. Alright, so there's a few videos, a car horn one and a few other bits and pieces there, so you should watch those. They're very good. So what's the Doppler effect about? The Doppler effect is about what happens to a wave when either the observer's moving or the wave's moving. All right, and so the Big Bang Theory one, watch that on, Sheldon will tell you, and what Sheldon says is the apparent change in frequency due to the relative speed between the wave and the observer. So in this case here, we've got the wave that's stationary, and so it's all sending out circular waves. What we've got is our observer down here, and our observer's moving through. So because our observer's moving through, the observer gets to the next wave earlier than he would have if he had just standing there. And there's more information than this in your note. Now, the alternative, of course, is that the observer's stationary and the source moves. So you can see this outer ring here, that outer ring, this one here, that would have been produced when the source was there. Then the source moves on and it would produce another one, and the source moves on and there's another one. And the source moves on and there's another one. Then it's here and it's produced that one, and then it gets here and it's now producing that. Now, you'll notice what's happened is with this distance here is shorter. And at the other end, this distance here is longer than for the stationary ones. All right, so here's our stationary ones. So our observer here, because these are closer together, they appear to be a higher frequency than these ones here, and that's the car horn Doppler effect. You heard that on the video when you watched the video. And so the frequency of that was quite clearly audible. You can see that it was different. Well, it turns out that the same applies for light. And with light, when we get the shorter wavelengths, which is down this end here, for light, that's what we would call the blue shift. Whoa. The blue shift, so as the colour moves towards the blue, or the frequency moves towards the blue, and then these ones down here where it's a longer wavelength, that would be our red shift. Alright, so you start, alright, this one here, so our wave is normally this one here in the green, Roy G Biv, alright. So we've got the green, and so if we've got our source that's moving away from us, which is this one down here, that lengthens out the wavelength, lowers the lowers the frequency and lengthens the wave, and so that frequency is more towards that red end. If the source is moving towards us, then that compresses that wave, higher frequency, and that then moves it towards the blue end. So that's a blue shift. All right, and red shift in particular is easily observed when we're looking at distant galaxies, because they're moving extremely fast. So their shift is quite easy to see. All right, and so again, well, that's stuff we did visit and do last year. All right, so then there's some text questions there on that stuff. So just again, make sure if there's some things that I haven't explained completely to your satisfaction, make sure you give me a yell. Make sure you watch the videos; they're quite handy. And then your text questions.